geometric. And as important as those, or more important, they come here numerical methods. Numerical. So we play with those three. I have been playing with geometry. They give you the global picture. Analytic, of course, I'm going to have to integrate. And now we go for numerical. Okay with that? Okay. So the first method that we always see as a numerical method is called Euler's method. Euler's method. And you are here in Ireland, you cannot say Euler or Euler or no. Euler. You need to talk the right way. Euler, right? Okay, he did a lot of stuff in mathematics, in math. Of course, he came up with this method not for the sake of a numerical method. He was not an engineer. He wanted to prove the existence of solutions to differential equations. So that's why he came up with the method. Okay, let's just take a look at the method. That's it. I have, let me put a differential equation right there. I have dy dx equals to f of x comma y equal to x plus y. And I also have that y of 0 equals 1. So these numerical methods are for what we call initial value problem, IVP. They solve initial value problem. An initial value problem has two pieces. An IVP, an initial value problem, has two pieces. One piece is the differential equation, the DE. And the other piece are the initial conditions. Is that okay? So the union of these two things make that one. And I can call it an IVP or initial value problem. So initial. And these ones are initial conditions. An initial condition, right? Okay. Let me see how this goes. Suppose the actual solution was like this. That is the actual solution to the differential equation. That is the integral curve. I would have solved that analytically, and you would have seen that blue line. That blue line better go through 0, 1. It better go through 0, 1. Let me put 0, 1 somewhere here. There is 0, 1. Right. You can see that I just moved the origin. Engineers feel like moving the origin anywhere they want to. Well, math people were like, we want the origin at the origin. But engineers move it anywhere they want to, and they're correct. I mean, you are your origin. Ultimately. Okay with that? Anywhere you move, you are at the origin. Okay. So that's pretty deep, actually. Okay. So I don't see the blue. Euler doesn't see the blue. Euler, the only thing that Euler sees, the method itself, it only sees a slope information. Okay, with that, only a slope information. So there was going to be a little slopey right there. That's the only thing that Euler sees. And what is the value of that little slope? 1. Because you will take the 0, 1 and plug it into the slope information, into that machine. That machine that I have upstairs enters order pairs and spit out slopes. Okay, and we love slopes. Okay. Yeah, we really love slopes. So right there is where everything is going to start. But in general, we call it x naught, and we call that value y naught. Y naught, x naught. But for us right now, this is the value 0, and that is the value 1 right there. Of course, Euler, the method comes with a step that we call h. We're going to move by h. and recalculate the slope. Okay, with that we move by h from x naught. So if we move by h from x naught, we just make a step that is going to go all the way to x naught plus h. Okay, with that it will go to x naught plus h. So somewhere there I will make a step. On the actual problem, I'm going to make step, let's say 0.1. The smaller the step, the closer you're going to be to the real solution. Okay, the smaller and the smaller the step. But I'll make a step, and I'm going somewhere there. I don't see the blue. I'm going somewhere there with x naught plus h. And of course, x naught plus h is 1. It's x1. So this I move by that much. And I extended that slope information up to a new point that I'm going to be right there and recalculate everything. Okay, well, I'm explaining the method. They will tabulate everything. The method will split order pairs. Okay, with that, let me just go right now, and I just see a triangle. I see a triangle right there. On that triangle, if I zoom to that triangle, that I see right there, here is my x naught. Here is my x naught plus h, which is x1. And then, of course, this is the h. And I know this value. Because this value is the value of the inclination, is the slope. And I know that slope better be given to me by f. And what am I plugging in general for this step? The 0,1, but the 0,1 is in general is x naught, comma y naught. The x naught, comma y naught, put it right there. The x naught, comma y naught, that's the slope information. So on that triangle that I'm building, the inclination, which is an extension of the original little sloping, it is f of x naught, y naught. Okay with that? Because that's the rate function. And then, of course, I need to know this leg. I need to know that leg. And I close my eyes, and I think of high school, and I think the rise over the run. Yeah. And what better be the rise if the rise over the run is going to be that? That's the rise over the run. This better be. That better be that, because the rise over the run better give me that. And now I got everything that I need for my next step. That is my next step. I just need the x component of that new step. What's going to be the x component? Well, it's 1 or x naught plus h. Okay, well I can go to x1 by doing x naught plus h. That's the formula right there to get the x component. And this is my first step. And that of course would be my x1, which is x naught plus h. What will be my y1? Yeah, although my y1 will be. Yes, yeah, I'm going there. I don't know if that's in Spanish. Almost came up. There. There. I got my x1, and you are correct. My y1 will be the sum of the two heights. One that I already have, which is the y naught. The other one is the h, f of x naught, y naught. So that will be my y1. So how do I get my, this is a recursive. It's ready for computers, this method. The x1 is x naught plus h. And the y1 is equal to y naught plus h, f of x naught, y naught. And that's the formula to get sorry. Those are the formulas to get the first step. But I don't really want the first step. You know that we're more ambitious than that. We want the n plus 1 step from the nth step. It's just changing those. Okay with that? So in general, when I come right here, making the picture, making the picture right there is, in general, I am sitting at xn, yn right there. I have a little slope given to me by, of course, the differential equation. dy dx, f of x, y. And then I'll make the extension to xn plus 1. And how did I go from xn to xn plus 1? Only by a silly h. Okay, without that step. And then I extend the slope to get my new value. I'm already at height yn. This is f of xn yn. This is my h, and this is my rise, h xn yn. So I have all the formulas right now to get my new order pair, xn plus 1, yn plus 1. The formulas are, the formulas that I will program on a computer would be xn plus 1. It's equal to xn plus h. Yn plus 1. It's equal to yn plus h times f of xn yn. And these are packaged like that. Ultimately, what do I get? A sequence of slopes, order pairs. Okay, well, I get a bunch of order pairs. And what the computer is going to do, the computer is going to smooth those things. Is that okay to give me a solution that it will get as close as I want to, as I just make h smaller? Okay with that? Okay. And this is very powerful. I remember that I was taking a class in aerodynamics, and I had to use this for a particular problem. Well, not really Euler, but a slightly more sophisticated version of Euler. But I started with Euler. So after Euler, in another class, you look at this guy, German mathematician, okay with that, from the 1900s, 1905, around there. And after that, you will see RK4. Another German guys, Branch Coda method. This is Euler-like. This is Euler-like. We use this one in that class. Is that okay? It's just a better approximation. Is that okay? But still based on Euler. Okay with that? Okay, so I'm very happy with Euler. I can explain Euler, and then when I run the Branch Coda, I don't need to explain it that much. It's a better version. Okay with that? Okay. So if I'm waiting for tacos at Torchy's, I have a napkin, and I can make that picture to myself. Is that okay? I'm bored. Okay, so now let's do it. Now let's solve the problem. Let's just get these numbers out. So then I will make the official table, because this is going to be tabulated. Let me see. The official table, I'll just put it there. I have the formula right there. The official table. Because the number one thing right here is to organize all the numbers. If not, you get just chicken scratch all over the exam, and I cannot find a thing. Okay with that? All of this is tabulated. So n, then there I'm going to put xn. There I'm going to put yn. There I'm going to put f of xn. yn, and here I'm going to do h of xn, yn right there on the official table. And then here I will put 0, 1, 2, and then we can start filling the table. N0 means that right there I want x naught and y naught. Can you whisper on your friendships here what you do for x naught and y naught? Everybody whisper? I hope that you plug in a 0 and a 1. Okay with that? A 0 and a 1. Because the initial conditions, maybe 1. The initial conditions are y of 0 equals 1. So x naught is 0 and y naught is 1. And then you go to get a slope information. Okay, can you whisper that on your friendship here? You're like, it's Friday, I don't want to. Yeah. I hope you whisper uno. Yes. Because you enter the equation. I am using the equation. I'm not. It's okay. That's the slope information. It's a 0 plus a 1. I'm plugging a 0 plus a 1 to get a 1. A rate of 1. 1. And then I'll go and calculate myself h times f of x naught comma y naught, which is one times 0.1, 1 times 0.1, and 1 times 0.1 is that one. I got it by doing 0.1 times 1. 0.1 times 1, right? Next. And now I'll continue to use I want to get myself x1. I want to get myself x1. x1 is x1 is 0.1. Yes. I heard 1 and I was like, okay, yes, 0.1. Because I get it by the formula that is right here. That formula is the 0 plus a 0.1. And I can actually put the next one right there just for fun. The next one is 0.2. 0.2. Because I'm moving by 0.1. Then I'm trying to get myself y1. I'm trying to get myself y1. And you know how to get y1. Y1 was, by looking at the formula, y1 was y naught plus h f of x naught y naught. And I have those on the table. I have already those on the table. This guy is 1. And can you see, you don't need a calculator on the exam. It's going to have nice numbers. Okay, with that, you don't need a calculator. 1 plus 0.1, 1.1. 1.1. And then the computer will plot those 2 other pairs. So, okay, we have 2 other pairs now. Okay, with that, let's just continue a little bit more. How do I get my hand on that one? Plug it in. I heard somebody saying plug it in. Yes, you plug it in on the rate function and you get 1.2. Because it's asking me to add those two, the rate function. And then I'm going to get myself the h times 1.2. H times 1.2 is 0.1 times 1 times 1.2. 0.1 times 1.2, which is 0.12. Thank you. Right there. And I can continue a little bit more to get the next one right here. Then of course, how do I get this guy? Yes. This guy plus that guy is the formula. Those two. That will give me a 1.22. 1.22. And then if I want to get this guy, that guy is, by the format of the differential equation, the x plus the y. Okay with that? Because that was the rate. So 1.42, 1.42. 1.42. Right there. And just for fun, this one. .142. Right there. And then of course, let me just do one more just for fun. But on the exam, I will stop right there. There. Okay with that? So 1 point for each answer correct. This one doesn't have partial credit. Okay with that? So make sure that you check every previous step. Okay with that? Because if you check, okay with that? On other problems, I do have partial credit. On all of the other problems, not on this one. Okay. Okay. If I were to go another line, which I will not ask, just for fun, you know that this is going to be a 0.3, and then the yn will be, the yn plus 1 will be the sum of this guy and that guy right there, the sum of those two. And then that is a 1.362, 1.362. And that's it, I'll stop right there. Three other pairs that the computer will plot and the computer will smooth. Okay with that? And then for that step size. For that step size. Okay with that? Okay? Okay. Can you see there is not much to it for Eulers? Oh, okay, no, there is more. There is more. Okay. There is more. Let me put this on the side. Let me put another equation. dy dx equals to x and y. Initial value problem. Y1 equals 2. They give me the age, so I can do Euler. I can do Euler on that problem and just do the table. But they want to ask me something a little nicer. Well, this is nice, making the table, but they want to ask me, we want to know if the value y1, really x1, y1, at the value x1, y1 that we will calculate, if this value will be an underestimate or an overestimate. Because we know that Euler is in a loose equation. The solution will come like this. The true solution will come like this. And then of course at once you are moving away from that solution. How can you get slightly closer by making the h smaller? But you're already diverging, not by a lot, but usually it's a problem of you're locally wanting to know that. So you can zoom in, okay, without making the h smaller and smaller. So in this particular sketch that I made, whatever was the x1, y1, it was an underestimate in my picture. So okay with that, okay. So who's going to tell you if you're underestimate or overestimate? Who comes to the rescue? Yes, the second derivative comes to the rescue. Because I want to know if locally there I'm concave up or concave down. Okay with that? I want to know if locally I'm concave up or concave down. Concave down. now that you're here with us, concave down in engineering will really mean concave. If we say that something is concave, it's definitely concave down. It's a synonym. And then concave up, it's a synonym of convex. So we don't use anymore the concave up and the concave down language. Engineers use the language concave and convex. Okay with that? Concave from concave down, like the natural log of x. The natural log of x is concave. Okay with that? The square root of x is concave over its domain. Okay with that? Okay. Okay. So that's it. I'll go for that. The second derivative. That's it. It's going to tell me all the information. I'll take the CD derivative of that product rule. And I proceed to plug in. I'm going to plug in 1, 2. I'm going to plug in 1, 2. That's the initial condition up there, all the way up there. So this is at 1, 2. So this is 1 times 2 plus y prime times 1. And my voice is changing out of the emotions. What is y prime? Dos. Y prime is 2. Okay with that? Because y prime is dy dx. And the rate function is x times y. You're not respecting the rate function if you cannot tell me that the answer is 2 for dy dx. Because you're plugging 1 for x times 2 for y. The differential equation is x times y. Okay with that? Okay, okay, okay. We love slopes. Yes, yes. So this is, look at the DE. Look at the DE of the way upstairs. Near 1, 2. 1, 2, that's a 1, that's a 2. So then we get 1 plus 2 plus 2 times 1. We get 4. 4 is greater than 0. So what are we? Underestimate. Because it's right there convex. So my slopey will come right under the convex function like that. I know what type of error I have. Okay with that? Okay? Okay. We're done with Euler. Okay. And then I can now go and solve an equation, a new equation. First order. First order differential equation. And what is the shape of the first order differential equation? It's a slope there, a y prime, plus a px times y equals a qx or a gx right there. That is, anything walking like this, she is a first order differential equation. And it's important to memorize that, definitely, because these equations might be constrained, but they show up a lot. Okay, with that, they show up a lot in a lot of applications. So they are super useful. They are super useful. One of them is, I think I gave you one some time ago that we plotted. Let me see. Some time ago, we went and we plotted this one with isoclines. Dx is equal to f of x comma y is equal to x plus y. And it was an initial, let's say we have an initial value problem right there above. That equation, 2 classes ago, I made all the isoclines. Okay, with that, they all look tilted. And I think they look like that. Okay, with that, all the nodes. Okay, with that. Now, we want to solve it analytically. Okay, it's not separation of variables. That will not work, separation of variables. So then of course, I'm looking at her. I'm sorry, equations are feminine in Spanish. Okay, I'm looking at the equation right there. I'm looking at her and I'm saying, well, I need to make it look in the form of the first order DE. So you can see that it's looking like a y prime, x plus y, and then what would I do next? To make it look exactly like first order DE. Send the x to the other side, send the y to the other side negative. And then I will know who's playing the role of px and who's playing the role of gx. So I go like this. So one more time. I go like this. Send the y to the other side, and there is the equation. As soon as I look at her right there, she looks exactly like that. Who's playing the role of gx? X. And who's playing the role of px? Negative 1. Negative 1 is playing the role of px. Okay with that? Okay. Now comes trying to solve this equation. Now comes the idea where I'm trying to solve that equation. That equation, the way it is right there, it looks like on the left hand side, it looks like a product rule ready to be born. Almost. Because can you see that I have a y prime, and then I have a y, and I have some plus or minus in between. Okay with that? And I remember the product rule. And the product rule looks like y1 prime times some sort of another function, y2, plus I leave the y1 alone. And then I'll take the derivative of the y2. Okay with that? So it looks almost like that. So who comes to the rescue? An integrating factor. Okay with that? An auxiliary function that is going to come in and is going to help me solve this problem. Functions are feminine in Spanish also. So she's coming in to help, and then she will go. Okay with that? Okay. So I call it mu. Okay with that? Mu. It's not a U, but it's a mu. You have to put your lips like a French man or a French woman. Mu. Okay with that? Okay. Okay. I know that because I speak Spanish to my children, but my wife only speaks French. And they make fun sometimes of my accent. No, they don't make fun of my accent. They look at each other when I speak French. Okay, so that's it. Can you see what I did? I multiply by the mu across the board. Okay with that? I multiply by the mu across the board. And then of course, that is the mu, that is the y prime. So all of these creatures better play the role of mu prime. Okay with that? Because I left the mu alone. I took the derivative of the 1. Plus, now I want to take a derivative on mu. Now I better have mu prime. Can you see the recognition that I need to make? Mu prime. This is the mu left alone. I took the derivative of the 1. Then all of these creatures better represent mu prime. All of that creature is going to represent mu prime to fulfill my product rule. Okay with that? Okay? And then of course I will come up with whatever mu needs to be. So let me just write it again. This is mu y prime plus minus mu y equals mu x. And whatever minus mu is, better be mu prime. So if minus mu is mu prime, right there, within the problem that I want to solve, I have this. Mu prime equals minus mu. Okay with that? And then of course, that's part of the problem also. Mu prime is d mu dx equals to minus mu. I'm trying to come up with what mu is. And then we know that we have a silly separation of variables within the problem. A silly separation of variables will come out with mu. This is a d mu over mu equals equals to minus dx. And this is the natural log of mu equal to minus x. Of course, minus x plus c. I have a whole family of integrating factors, but I only want one. I don't need all of them. So then of course I solve for mu. Solving for mu here is e both sides. And then mu comes out in full splendor right there. That is the integrating factor that I need. Or any constant to that, but that's the one I want, the super clean one. So that's it. You are e to the minus x times y prime. You are minus e to the minus x y equal to e to the minus x x. Can you see that product rule got fulfilled? That product rule was fulfilled. If you look at it, y prime times e to the minus x, then you take the derivative of e to the minus x, which is minus e to the minus x, and then you get the y left alone. Okay, well that is a product rule. So next, I'm going to, that looks like a telescope, an open telescope. I'm going to close it. Okay, with that, I need to close it. That is the product rule of two functions. Which ones are the functions? E to the minus x and y. And I'm going to close it right now. The notation will be e dx of e to the minus x times y equal to e to the minus x times x. Right there. I'm almost there. I'm almost solving the problem. I'm almost done. What would I like to do next? Integrate both sides. Okay with that? What's going to happen on the left hand side? I'm taking an integral of the derivative itself. Is that okay? On the left hand side is an integral of the derivative. So I agree with what you told me. It's itself. But then on this side, I'm going to have to take an integral, and of course I'm going to have a plus c right there. I'm integrating the right hand side. Is the right hand side nice? What method of integration? By parts. So I'll do that super fast. I'll try to do that super fast. If I make a mistake, you'll correct me. But it's x e to the minus x dx, u x du dx, dv e to the minus x, v minus e to the minus x, uv minus the integral of v du. So all of this turns out to be minus x e to the minus x minus e to the minus x. Check me on that. Okay, so then I'll put that right there, e to the minus x, y equal to minus x e to the minus x minus e to the minus x plus c. And then you send that e to the minus x to the other side, dividing, and then you have y with you. So I would have solved it analytically. Not the initial value problem yet. Not the initial value problem yet, but at least I have the family of integral terms. Okay, with that, all of those are the integral terms. Now I need to remember that I had an initial condition. I don't remember what it was. What was it? I can look really fast. The initial conditions were
y0 equals
yes, y of 0 equals 1. So that's it. I will use that right away to find the constant. Only one of those integral terms. So it's an IDP, y of 0 equals 1. So I proceed to plug in on the last answer. 1 is the y is 1, minus 0, minus 1, plus e to the 0, c. So c becomes 2. Okay with that? 2. So then I I plug in my 0 and my 1, that becomes a 2, right there. And then I want to check the solution. Super fast, I want to check the solution. This is an equation, this is a differential equation. If it's an equation, I can always check the solution. The original equation was y prime minus y equals x. Right there. Y prime minus y equals x. I can go and plug in. The solution is y equal to minus x minus 1 plus 2 into the x. I can plug all of this right there with parentheses. That is the y. And then I'm going to calculate myself the y prime. The y prime is minus 1 plus 2 into the x. So there I have a minus 1 plus 2 into the x. All of this right there for y prime. Right next to it I have minus x minus 1 plus 2 into the x. Can you see that everything is, I'm plugging in. Everything is going to cancel. Because I have a negative right there. And then I got minus x, which is x right there. So a full circle.